In example 15.3, we get an indication here with the Olmstead Bridge about how we can use a combination of a method of sections and method of joints to judiciously get to what it is that we're after. And in this problem, we've been asked to find only three member forces. Those forces are the force in member AG, that's the end post, in CG, that's the first diagonal in the web of the truss, and then in member GH. And whenever I'm asked to find only three member forces, I'm usually thinking about method of sections right off the bat. However, in this case, it doesn't really work so well because a single method of sections would maybe take us through this second panel. That would expose two of the members of interest. If we came at a diagonal, another possibility that would expose the same two but wouldn't still get us to the third one. And a method of sections that actually cuts through and around joint G, well, that's really just method of joints, and there's initially four unknowns there, and even though we can find member BG very easily by going down to joint B, we're still stuck with having too many unknowns. So this is a case where we're not going to be able to just do one and get out of here, so to speak. We have to do more. As well, we're going to have to find ultimately the reactions probably to get through this. So that's what you see here in the first step. You've been given 124 kips upward reaction for AY in the problem statement, but if you take a look here, you can see then with the global free body diagram the actual details of that calculation to find A sub y, and indeed that it goes 124 kips upwards. So now it's just a matter of strategy of being as efficient at this as possible. And I take a look and I say, okay, I know now what AY is. I've got a trivial equation to find AX, and in this situation then AX is exactly equal to 0. And so that says that if I were to go in and look at joint A, that I'm only going to have three non-zero forces there. I've got the upwards reaction of AY of 124 kips. That now in a sense is given. We've already found it, and we already know that we've got or not know, but we can anticipate that our member force AG is going to have to be directed downwards so that it has a vertical component to oppose the 124, and then likewise because AG then has a leftward component in this free body diagram, that means that AB would be to the right. We don't need that one as far as we know right now, but that at least makes for a complete free body diagram, and that part is certainly important to have. Right? So all we need to do then is sum forces in the y. Let's take upwards positive, so we have 124, and then minus the y component of AG. So we do need to know what that orientation is. That's an 18 run, a 24-foot high rise, and so what is that? That's a 6 to 3. No, if I divide by 4, what is that? Divide by 4. I don't like that. Divide by 3 here, I get how about just dividing by 6? If I divide by 6, I get a 4 and a 3. Hey, that's in essence, our AG is a 3, 4, 5 triangle. And so that vertical component here then will be 4/5 of AG. Set that equal to 0, so therefore AG is equal to 5/4 times 124. And 1.25 times 124 is going to be 155. Equals 155 kips total, and as shown, that would be in compression. So that was one of our tasks, was to get AG. I'm going to go ahead and write that right on up here on the drawing, that we have 155 kips of compression for AG. Now, whether I'll reuse that or not depends a lot on the next free body diagram I take. I love parallel chord trusses for a whole lot of reasons, one of which is that their solution or analysis of them tends to be fairly easy and straightforward. I like taking method of sections all the way through the panel, usually staying in the panel. It doesn't have to, but oftentimes that's what I'm going to do. Right? So for that method of sections now, let's get the free body diagram drawn. I'm going to take the left half for no particular reason. It might be more or less complicated than if I took the right half. Oftentimes the way I make my choices is based upon what's going to look complicated and what's not. And I'm not trying to get this entirely to scale. I just need to get this conceptually drawn in here. And since I did not cut now member AG, I've gone back to the original drawing here. All I have to do is get my reaction of 124 up in, and then at joint B we've got an applied force of 80. We have member BC, which we've not calculated yet. We've got member GH. We're looking for that one. So that's our top and bottom chords. Notice they sort of look like they make a force couple, and indeed that will actually be kind of an important, useful thing to think about. And then I have member GC, and I might as well think a little bit ahead about whether that's going to be in tension or compression. Note that in this free body diagram, I got 124 up, 80 down. There's going to be a net of 44 going up, and so that means that GC has to have a force directed down, and on that free body diagram, going downwards would actually indicate that it's going to be pulling away from the free body diagram or in tension. And actually I've already just written what that equation of equilibrium is going to look like. Sum of forces in the y, again take upwards positive. I have 124 up, minus 80 down, and then minus 4/5 of CG. It turns out to be of a similar orientation as member AG, and that has to all equal 0, so therefore CG has to be equal to 5/4 of the net of this, 124 minus 80, so that's 44. I might have said 24 earlier, I'm not sure. And I can do this one in my head. 44 divided by 4 is 11 times 5. That's 55 kips. And the plus sign in this equation indicates to me that I assumed the correct direction. And that direction in this case is pulling away from the free body diagram, or CG is equal to 55 kips tension. So we got 2 of the 3 requested quantities. And the fourth one, which was GH, I can find by getting rid of CG and BC by simply summing moments about where those two intersect at, which happens to be joint C. If I sum moments there, I have nothing but known applied forces and my unknown that I'm interested in. And so let's see what that would look like if we sum moments about point C, taking counterclockwise as positive. I like to say take the same direction as my unknown force. And so that has a 24-foot moment arm with respect to C, minus 124 times 18 times 2, so really 36 foot for its moment arm, and then plus 80 times 18, all set that all equal to 0, and take the known stuff to the other side, so that's 124 times 18 times 2 minus 80 times 18. I do get a positive number, that's 3024, and then divide by 24, and I get 126 kips. Again, the positive sign indicates that I assume the correct direction, but as shown, it's pushing on the free body diagram, so therefore that will be in compression. And I'll come right back up to the, in this case, the original drawing, and I'll place these numbers in here. We had that CG was 55 kips in tension and 126 kips for the chord, top chord. That was also, or that was in compression. And so if I were doing all the rest of the work for this particular analysis, I would then take I'd go find all the rest of them, and then I would redraw the structure and put just only the applied forces and the resulting internal forces superposed on top as my final summary of the work.